Hello, welcome back. Welcome to the second part of the video series on the Intel Distribution for OpenVINO toolkit. In the first part, what I've covered is the application or what is OpenVINO and why exactly it is used for, and an overall flow, like how everything happens, the concept of intermediate representation layer, like it is essentially an inference engine and what all are possible. In this video, what I'm gonna show you is a very quick walkthrough on the Intel IoT Devcloud platform and how we can, just go through the samples and get an overall understanding about the different type of results that we can obtain after submitting it to different edge nodes. Also, we are gonna see what are the edge nodes that are available to us, and by the end of the video, it will be much clearer that like if you have a model and if you have a trained model and if you have passed through the model optimizer tool to get the intermediate representation layer, after that you can simply deploy this thing to the Intel IoT Devcloud before buying the actual device, the physical device. Before buying it, you can actually test it how your model is gonna work in the actual edge device is in the Devcloud platform, and based on that, based on the inference results that you obtain after performing these computations in the Devcloud platform, you'll have an overall idea like what device should I go for depending on the use case. So let's begin. So this is the overall platform that we refer to as the Intel Devcloud for the edge, or in common terms we call it as the Intel IoT Devcloud. Here you have examples, you have the overall overview for OpenVINO, you have the Devcloud overview, you have lots of tutorials that you can browse through, understand the codes, each and everything is possible. And finally, you have some smart video workshop as well. So what happens in this Devcloud is that it provides you an exactly same kind of environment that we require, or rather that we require during the developmental phase of our application, because every time it is not possible to have each of these edge nodes as a physical device with us. So before you want to really deploy to a physical device, you might want to simply try the Devcloud out and understand like how it was, what are the limitations, how much performance you are getting on a physical device. Using Devcloud, you can figure each and everything out. So this is a very cool tool to explore OpenVINO as a whole, as well as the Intel platform. So what we are gonna do is that we are gonna head to the advanced section, in which there are a couple of sample applications that has already been preloaded in the Devcloud. And in this case, we are gonna have a look into the accelerated object detection. It will be available as a Jupyter notebook. We will be going through this example. We won't be doing the coding part of it. We are just going to understand the performance at each of these edge nodes and why like OpenVINO is so important, because you write one piece of code and deploy it anywhere. So I have already opened this as a Jupyter notebook. It is available, view code in Jupyter notebook or demo. And this is the Jupyter notebook that you get in the Intel IoT Devcloud platform. So what I'll do is that I will quickly follow the steps that we have seen earlier in my slides, in which I have mentioned what all the processes are involved for inferencing on OpenVINO, using OpenVINO rather. So the first step is that we gonna download a model. In this case, we are going to download a MobileNet SSD model. We are gonna use the model downloader tool that comes with OpenVINO. By the way, we are gonna use it to download our model. So after that we have downloaded, you might remember that we need to convert this model to a OpenVINO format kind of thing, which is the intermediate representation layer, which will generate the XML and bin file. So we are gonna run the model optimizer, which again comes as a part of OpenVINO, and pass the raw model and define some few configurable parameters and build the necessary iron layer. This may take some time. We are gonna build the IL layer for float FP32 as well as FP16. So I'm just gonna run it again. FP32, it has created a file which is mobilenet SSD XML and mobilenet SSD bin. Similarly for FP16 also, it has created the file as SSD and the XML and bin file. Next, we are just simply gonna submit this to the different edge nodes. Now here where things are very interesting, really. So once I run this job inference, which is essentially a GUI, which is a GUI in which all the nodes are mentioned. So you can have a look as 6th generation Intel Core, Intel FPGA, 6th generation, like all these are mentioned clearly, and the target architecture. So you have the Xeon CPUs, we have the VPU acceleration card MX8, you have the FPGA, the RDR10 FPGA, the Intel NCS2, all these options are available for us. So what I'm gonna do is that I'm gonna deploy one in a Xeon CPU, another in the Intel HD graphics 630, one will be on NCS2, and one will be on the MX8 VPU acceleration card. So let me quickly select whatever node I want. I will just click on the submit button and then the process will begin. So I will just select the node at Intel CPU, and I am gonna head to the VPU. I am gonna submit another job. I'm gonna head to the 8th generation Intel Core. I'm gonna submit it to the GPU this time. And finally, I'm gonna submit it to the Intel FPGA. So internally, it uses the qsub command in Linux. This is a qsub command, and it runs a shell script, which is available in the code section. So if you have clicked in view code in Jupyter Notebook, you will be able to see it, which is available here. I'm not gonna go through this thing. So in the meantime, this process happens, or while the job execution happens, which may take a bit of time because depending on the node's availability, it will be deployed. I'll be just walking you through another article of mine where I have actually covered this most of the thing in full details. So this is a Medium article which was written way back in May 16th of May 2019. Object recognition with Intel Distribution of OpenVINO toolkit. Here you can find in a descriptive way like what exactly is OpenVINO and why it is used and how I have written the code and everything. I've also mentioned the architecture of OpenVINO, which I have shown you in the earlier slide, as well as the overall flow. Like you have a camera, you have a video frame, then you pre-process the image, pass it through the inference engine, obtain the resultant array, superimpose the resultant data with the original frame and get the output. So it is implemented in Python. You can implement in C++ as well. I have segregated into two files, which is main.py and detect.py. Detect.py is actually where the main thing happens, while main.py is just a driver code. You can go through the code, you can get an overall understanding. It's explained in full details. Each and everything is explained fully, and the code is also hosted on GitHub, and you can simply go through it. Finally, because since you want to run this code in your system, you might want to download OpenVINO, so you can click on this link to download the OpenVINO toolkit, as well as you can download the pre-trained models using either the model downloader tool or by simply clicking on this link, and the OpenVINO model zoo, which consists of many pre-trained models, are also available in a GitHub repository. So you can definitely go through the article and get an overall understanding as in what exactly is OpenVINO and how actually we can implement this on a real physical device. So this has been running in my system. I have implemented this code in a physical Intel NOC, where I was able to achieve FPS of somewhere close to 60 to 70. So let's head back to our jobs and let's have a look. So job ID, that is the first one, the Intel Xeon CPU has completed. You can see it has taken a total time of 26 seconds. and this is the inference time, and a rendering time of 41 seconds. So you can see the inference is actually faster than rendering. In the second job, which was on Intel MX8 VPU, which is a vision processing unit, there it has taken 7.3 seconds. It actually, what happens, like, it consists of 8 VPUs. It consists of 8 VPUs to process all the frames parallelly to each other. So that's why it's so fast. We are gonna display the output and everything, and it's the rendering time is 37 seconds. The third one was on 8th generation, which is on the GPU, Intel HD Graphics 620, and here it took 40.6 seconds with a total rendering time of 42 seconds. And finally, we have the Intel FPGA, where again you have got awesome results of 7.0 seconds only for inferencing the video, and a total time of 37 seconds for rendering it. So once I plot the results, then you'll get a feel of exactly what it's all about. See, the Xeon, like the graphics for some reason has a worst performance, and the MX8 VPU or the FPGA has the best performance in terms of inferencing. In terms of FPS, again, we got the very good results in FPGA as well as in the MX8 VPU card. And finally, which is around 409 FPS frames per second, 429 frames per second. And finally, in job ID, which is 166, which is a GPU, we have a FPS of 73.96 seconds and 115.38 seconds in an Intel Xeon CPU. So over like by this demo, you can get a very quick understanding like how does the performance matters at the edge level. This is not being done in the cloud, although it's now being done in the cloud. But what I mean to say is like it's actually deployed on a physical device where this processing happens. So this is kind of very interesting. And imagine like if you are deploying a smart camera where you are having this MX8 VPU acceleration card, you are going to get 409.28 FPS depending on the model. Can you imagine that? In 7.3 seconds, the entire video frame is processed. It will be very fast. So, and it's all happening at the edge level. The AI on edge concept gets real here. Well, hello there. Thank you for watching this video. I hope you like this video, and please do share, subscribe to my channel, and please provide your valuable feedback in the comment section below. All the GitHub code and the link to the Medium article is mentioned somewhere in the description, so make sure you have a look into it. I have also mentioned the download link for OpenVINO, so you can download OpenVINO using that link, and then you can readily get started in your system locally. So, and also if you can request for Devcloud access, for which the access link, like where you need to raise the request, I have also mentioned that below in the description. So you can get started pretty much soon using OpenVINO. I'll be posting more videos soon. Probably I will be posting one more video on OpenVINO sometime in the upcoming weekend, because that is the only time I get for doing stuff related to YouTube. And what I'll try to cover in the upcoming video is something about the code that I have gone through. I didn't explain the coding concept out here in this video because that is something which I was not intended to do in this particular video. I'll be doing that in the upcoming video because that is gonna take a bit of time. And finally, in the upcoming few weeks, I will try to cover something known as sensor fusion, in which I will be using this stack, which consists of an Arduino Uno, LoRa shield, and GPS shield, and base shield for connecting different sensors. I'll be using all this to send data via LoRaWAN to the MQTT broker, and then writing some cloud services to process that data. that will be a great topic, and I'm trying to cover that in the upcoming few weeks or so. So thank you again. Meet you soon, and stay safe and stay in your home.